I hope I am audible. So this is me, Tosif Alam, and we are having the course Introduction to Astrophysical Fluids. So let's start today's session now. So I hope till now everything we have covered is okay and available by you, and you have an good and open access to the course. So let's discuss today. So for that, let's wait for some time for others to join. Okay. Okay, so let's not wait any further. Let's just start the session. So this is the last assignment, assignment 9. So okay, last time we have solved the assignment 9. So let me know if you have any problem in any section of that we will try to answer. So let's look through the assignment 9 from the last time. Okay. assignment 11. It's not 11, okay. So I hope I'm audible. So the first questions in this is actually a problem. Yeah, so assignment 11, okay. So the question number 1. So we'll start with the question number 1, that for alpha band waves which is true. Okay, given is option A, omega is root over k parallel square plus k perpendicular square b naught. Option B, omega is equal to k perpendicular b naught. Option C, omega is root over 1 minus k square b naught. And option D, omega is equal to k dot b naught. Okay, so let's check which one should be correct. So we know answer. So what do you mean by alpha band mode? Okay, so you know that wave mode omega A, that is equal to k parallel b naught, is called alpha band mode, right? And the above relation, this relation requires k and b such as k is equal to k sorry k is equal to k perpendicular e1 plus k parallel e2 and b is equal to b naught, sorry, not, maybe I should write in x and yz form, okay, so then it will be yz, this will also be yz, okay. So the wave vector is parallel to magnetic field, so the wave vector is parallel to magnetic field and appearing, so only k parallel is appearing in omega A, right? So one can write that omega A is what? So omega A is basically k dot b naught. What are the options again? Achha, b naught is small. Yeah, so b naught, because it will be then k parallel B not, obviously. So the option D is the right answer. So D is the right answer. Okay. So the next question in question number 2 is in magnetoconvection instability can occur. Instability can occur from growing oscillations under which conditions? So you have these conditions. Let me read out the condition. The condition A is if magnetic diffusivity is greater than thermal diffusivity. Okay. So option A, magnetic diffusivity greater than thermal diffusivity. Okay. Option B is magnetic diffusivity less than thermal diffusivity. Option C is this equal to this. Okay, basically. And option D is always true. Okay. So the right option is option B. What? Option B. Answer. Option B is right answer. Okay. So question number 3 then darkness of sunspots is due to darkness of sunspots is due to what? The inhibition of thermal convection by the magnetic stress inside sunspots. Okay. Inhibition of thermal convection by the magnetic stress by the magnetic stress inside sunspots. Okay. Inhibition of magnetic stress by the thermal convection inside sunspots. Okay, this is the right option. Okay. Option B is not correct. Option C is not also correct. You already have the option, so I'm not writing that. Answer option A is correct. Answer. Just ask me if you are in doubt. I don't need to write. I don't feel I need to write all this. Reynolds number represents. Reynolds number represents what? The relative importance of nonlinear effects. Relative importance of nonlinear effects to the viscous effect. To the viscous effects. Okay. Then the pressure force to body force. So yeah, this is the option B is again wrong. Option C wrong. Option B is saying the relative importance of the pressure force to body force. That is not number, right? The ratio of the largest to the smallest scale of turbulence. This is not also the Reynolds number. The time to attain stationarity. This is not so. Reynolds number is basically relative importance of nonlinear effects to the viscous effects. Okay. So how the fluid is relatively nonlinear. Okay. Then the viscous effect is already acting on. Right. So option A is right answer. Question number 5 is again saying which of the following are required conditions for statistical homogeneous turbulence. Required conditions for statistical homogeneous turbulence. Okay. Option A is any partial time derivative always vanishes. Correlation of two quantities. Correlation of two quantities at two different points. Two different points depends only on the distance between them. Option C, average velocity is 0. Option D, single point statistical average of any quantity is constant for the system. Constant for the system. Okay. So option B and option D are the right option. I will explain that if I have time. D. Alright. Question number 6 is if the largest vortex of turbulent system is roughly largest vortices of a turbulent system is roughly 10 to the power 5 times greater than the smallest, it is what will be the factor by which the velocity of largest eddies will be greater than that of the smallest eddies. Pardon my writing. Option A is roughly 46 times, roughly 110 times, roughly 17 times, roughly 170 times. Okay, so let's do the math. So for stationary turbulence, VDQ VLD is actually VLQ by LL. So VL by VD is LL by LE. Okay, obviously. So from here we will get that VL by VD is approximately LL by LE to the power 1/3. Right. So it is given that it is 10 to the power 5. So 10 to the power 5 times 1/3. Right. So how much it is? So this is like, okay, 10 to the power 3 to the power 1/3, 100 to the power 1/3, right? This is 10 times how much? 100 is near to the 4 and 5. Suppose this is 4.5. So this is like, okay, or 46. 4.6. Okay. By value. So A. So option A. 46 times A. The correct answer. I think you are getting how we are doing this. Right. If you have any doubt till now, you can ask me. And otherwise, we'll proceed. Feel free to ask me in the next session also. Question number 7. Inertial range in energy cascade is length scale where energy is injected, length scale where energy is dissipated. See, range of length scale range between energy injection scale and dissipation scale, and option D is macroscopic length scale. Macroscopic length scale. So it is actually option number 3. Answer C is right answer, right? Okay. Think you understand how we are getting that. If you have any doubt, feel free to ask me. Okay. So I hope till now everything is okay. So till now we have done only 2 maps Hearthstone for the Alpine wave, Alpine mode. I'm not writing the whole options because you already have all the options in assignment. I'm just trying to help understand the topics. Okay, that's all. So question number 8. Question number 8 is for an isotropic and homogeneous turbulence, which of the following relations is correct? Which of the following relations are correct? Option A, K proportional to Ek to the power minus 5 by 3. Option B, K proportional to Ek to the power 5 by 3. K proportional to Ek to the power minus 3 by 5. K proportional to Ek to the power minus 2/3. So the question is that for an isotropic and homogeneous turbulence, which of the following relations are correct? So if you have followed the lecture note, you will know that for an isotropic and homogeneous turbulence, the relation that it holds is actually the power. Okay. Yeah, and that is actually right answer is actually this. The power is minus 3 by 5. The power law, it follows is minus 3 by 5. So option C is right answer. Okay, so that's how we get to that one. Option 9, what is saying? For a low beta MSD plasma. So for a low beta MSD plasma, the phase speed of fast magnetosonic mode is sonic mode is option number A, equal to sound speed Cs for transverse mode of propagation. Option B is equal to sound speed for longitudinal mode of propagation. Option C, less the sound speed for longitudinal mode of propagation, or option D is equal to Alfvén speed for transverse mode of propagation. So it is actually option D because it always propagates at Alfvén speed. For low beta MHD, phase speed most is Alfvén mode. So option D is right answer. Okay. I hope you're being able to understand. So the last question is question number 10. In MSD, a force-free magnetic field is always constant. Option B is parallel to the current. Option C is always rotational. Option D always satisfies Laplace's equation. I think you have come across this. At how hard the force-free magnetic field will be. Okay, so in MSD, the force-free magnetic field is actually parallel to the current. Okay, so this is actual option B. So option B is the right answer. I think that's all. Let me know if you have any problem in anywhere. I'm waiting for some time to get your answer. So meanwhile, just let me do one thing. Maintain. Okay. The previous day assignment solutions. So, and this is today's assignment 11. So for alpha and beta, which is true, so option D is true because of this magnetic convection instability can occur from going oscillation when magnetic diffusivity is far less than thermal diffusivity. Option 3, darkness of sunspots is due to only inhibition of thermal conduction by the magnetic stress inside sunspots. Reynolds number represents relative importance of nonlinear effects to the viscous effects. Required condition for statistical homogeneous turbulence is correlation of two quantities at two different points depends only on the distance between them. This is a very important fact. And single point statistical average of any quantity is constant for the system. Okay. Please try to remember these two, very important. Option C is largest vortices of a turbulent system is roughly 10 to the 5 times greater than the smallest it is. Then what will be the factor of by which velocity of largest eddy will be greater than? So vortices given, so what will the velocity? So we know that the velocity divided by the vorticity, okay, is always constant, roughly constant, largest to the small. So when it goes as one third velocity to the vortices, then it becomes basically 10 to the power 5, cube root of 10 to the power 5. Okay, that's all. Cube root of 10 to the power 6 is how much? 100. So obviously it will be like less than or half of 100. That is why it is 46. Okay, so you can guess like, okay, so what will be the cube root of, not like this, what will be the cube root of 10 to the power 5. Okay, it's like a easy math. Commas 46. So inertial range in energy cascade is length scale where energy is injected or length scale where energy dissipated. Length scale range between energy injection scale and dissipation scale, magnitude, macroscopic length scale. So it is option C. An isotopic and homogeneous turbulence, which of the following relations are correct? So the power law follows minus 3 by 5. So obviously option C is the right answer. For a low beta emission plasma, the phase speed of fast magnetosonic mode is actually it is equal to alpha speed because it is at low beta emission. So phase speed mode is alpha mode. So and in emission positive magnetic field is always parallel to the current. So be the right answer. Okay. So I think we can also export then this export and the best quality. I hope it's getting updated. Let me check. Okay, and you have there. Okay. Okay. So I think everything is okay. So you're reaching very near to the completion of the course. So I hope you have a good exam ahead for those who are giving exam. So, yeah. That's all from now. Thanks for this special session to attend. So the next session will be our last session on 22nd October. So hope you guys will be there. Okay. Okay. Sabak hai. Have a good night. Okay. So everyone come. So this is assignment number 12. Okay. So I hope you can see my screen. Today is the last class basically. So, okay. We'll just quickly look through the assignment question. Okay, so the first question goes as the terrestrial magnetic field cannot be ferromagnetic origin because Earth's rotation is too weak to sustain a ferromagnetic field. There is no ferromagnetic material in the core of Earth. Temperature of core is well above Curie temperature of any known ferromagnetic material. Material in the Earth has its own magnetosphere. So obviously the terrestrial magnetic field cannot be a ferromagnetic because terrestrial magnetic field means the terrestrial based elements, okay. So like the Earth's Earth's land, okay, like Earth's surface, that magnetic field, because obviously the temperature of core is well above the temperature of any non-ferromagnetic material, right? Okay, so the turbulence and viscosity is responsible for oscillation of main frequency stars. The solid body rotation in the slowly rotating stars, emanation of the solar wind, option D, fragmentation of interstellar clouds. Okay. So turbulent viscosity responsible for, basically it is turbulent viscosity. We have discussed the viscosity in our earlier discussion session. So I am not describing that again. Unless you have any problem in understanding any part. So turbulent viscosity is responsible for basically solid body rotation in the slowly rotating stars. I think we have done this. I've done the assignment earlier. Okay, so yeah. Reynolds stress is 0. So question number 3, let's do next. Reynolds stress is 0 and we consider turbulence of an incompressible fluid. Okay. Option B is velocity at each point of flow fluid is uniform. Fluid is rotating in magnetic field and the molecular viscosity of fluid is 0. Okay. So Reynolds stress is 0. When it is 0? When velocity at each point of flow field is uniform. That is when Reynolds stress is 0. This is all directly from the lecture notes. Okay. I will describe if any math arises. Question number 4 is Irosnikov Krishnan phenomenology is valid for isotropic MSD turbulence with a non-zero mean magnetic field. An isotropic MSD turbulence with non-zero magnetic field, hydrodynamic turbulence, isotropic MSD turbulence with zero mean magnetic field. Okay. This is also a direct straightforward answer. I just knew Kaizen field is valid for only isotropic MSD turbulence with a non-zero mean magnetic field. Okay. Alright. Then question number 5 is energy cascade in inertial MHD turbulence is due to conjunction of smaller eddies into larger ones. So the interaction of galvanic wave packets propagating in the same direction. Fragmentation of larger eddies. Fragmentation of larger eddies into smaller ones. Option D. Interaction between counter propagating galvanic wave packets. Okay, so I want you to okay. So interaction between counter propagation. Okay. So what would be the right answer? So interaction. Okay. Yeah. So I think this can be yes. So energy cascade in answer energy turbulence is due to only interaction between counter propagation alpha wave packets. The interaction of alpha wave packets going in same direction. This could be in the same direction or same direction. So the right answer. Question number 6 is what is strange about terrestrial magnetic field? It has lasted only 10 to the 5 years which suddenly it had lasted much longer than 3 times 10 to the power 5 years. Indeed, it is abnormally strong at certain latitudes. So basically, the terrestrial magnetic field. So you know, terrestrial magnetic field exists now. So it must be very old, older than 3 times 10 to the power 5 years. That is 0.3 million year. Okay. So option C is correct answer. Obviously, it doesn't feel suddenly. We know the North Pole, South Pole changes over time, but not like flipping. So a steady magnetic field which is symmetric about an axis can never be sustained by a steady velocity field which is also symmetric about the same axis can be sustained by a steady velocity field which is also symmetric about the same axis since it can be sustained only with the velocity field is not steady, can be sustained by a steady but non-axis symmetric velocity field. Okay, so these are all right answers. Okay, so like to see that the question is steady magnetic field. A steady magnetic field which is symmetric about an axis. Okay, so let's imagine a steady magnetic field which is symmetric, okay, about an axis. So it's like, okay, suppose uh, suppose it is like this. Hmm. Okay, so this is the axis. The magnetic field is symmetric about the axis. That's what is what it is. It can be look like this. So the magnetic field, the field lines. Okay, this is the B. Okay, so the question is that steady magnetic field is symmetric on axis. So what are the possibilities? Can never be sustained by a steady velocity field. It is also symmetry. Uh, like if the velocity field is also along the same direction, so it cannot be sustained. Okay, obviously it cannot be sustained by a steady velocity field which is also symmetric. Okay, because the V cross B, the V should be in parallel. Okay, not perpendicular. V should be parallel, not perpendicular. Sorry, wrong choice of word. V should be perpendicular, not parallel. V should be parallel, not to B. Okay. Can be sustained by steady velocity field which is also symmetric. Okay, this is the same. Can be sustained only if the field is not steady, so not this. Can be sustained by steady but non-axis symmetric velocity field. Yes. So it can also be sustained or B can be non-axis symmetry like perpendicular. Okay. So option A and D are right. Okay. So let's go to the next question. Consider that there is no plasma motion. Motion inside the interior of Earth. Look at time. Earth core radius is 3486 km. Electrical conductivity of Earth core in C units. Okay. Then what should be the year? Option A 3 into 10 to the power 5 years. Option B is 10 to the power 11 years. I can say 3 into 10 to the power 23 years, something 10 to the power 3 years. Okay. So then what would be the magnetic decay time? Okay. So magnetic decay time. So radius is given and conductivity is given, right? The earlier question, there is a question now. (1965) minus manual. Okay. So for this, use the equation. We know that the dynamic field, um, magnetic field evolution equation is del V del T is eta del square B, right? And that is because that is approximately, we can say that, so that approximately we can say that this is B by tau, the characteristic decay time. Okay. So then is eta B, because it is del to be del square, so beta by L square, right? So then we will get that BB cancel out, we will get that tau is equal to what, L square by eta, right? So for Earth, how can we calculate? So to calculate, we know that eta is equal to, for Earth, eta is equal to c square by 4 pi sigma, okay, the electrical conductivity. So the value of electrical conductivity is given at 16, right? So this is linear equation 1, this is equation 2. Given electrical conductivity is 10 to the power 16 in CGS, right? So like CGS units, so suppose we will do it in CGS unit then. So eta is equal to, this is anyway in CGS, so eta is uh, this, right? So if we combine this equation, two equation will get, combining 1 and 2 will get what? Tau is equal to L square by C square into 4 by sigma. So basically 4 by sigma L is by C square, right? Sigma is given. Okay. Other constant C is also, C is just time. Okay. So then L is how much is given? 3486 kilometer. 3486 kilometer. So per centimeter is 10 to the power 5. Right. So then 3486 into 10 to the power 5 centimeter. Right. Tau is equal to 4 5 by 10 to the power 16. L square is 3486 10 to the power 5 square. See the light speed 3 into 10 to the power 10 square into 3 into 10 to the power 10 centimeter, right? So how much we will get? So 4 times 3.14 is 10 to the power 16. This is about 3.4 to the power 10, right? 10 square and then 10 to the power 8 10 to the power 16, and here we will get 9 times 10 to the power 20, like 10 to the power 21. So if we calculate this, 10 to the power 16, 32, 34, 14. Okay. To 13 or 13. So it will shown as 34, 21, 10 to the power 14, right? 10 to the power 14 seconds, right? So, okay. So if you convert that to year, so you need to like divide it by 3 into 10 to the power uh, 7, right? How much? 7. So then to the 13, 3 into 10 to the power 6 years, right? So yes, so this is like okay, yeah. So this is about, so nearest option is option A. So nearest option is A. Okay, so then option A is the right answer. It is nearest. Okay, so let's move on to the next question. So question number 9 is saying that in a turbulent dynamo, colloidal magnetic field can generate a toroidal field by helical turbulence. B. Differential rotation. C. Magnetic diffusion. D. Statistical fluctuation. Okay, answer. So there are two kind of magnetic field. You must have heard that. Like one is toroidal. Okay, so toroidal is actually the magnetic field in a toroid. Okay, so let me draw you a figure. I think I understand. So a toroid. Okay, so how can I draw a toroid? Suppose this is the toroid. Okay, and the field lines are centered. And the field lines are centered like this in a toroid. Okay, I think the back you won't see the back, but it is connected. Okay, so so this is like a toroidal magnetic field. So magnetic field in a kind of toroid. Okay, kind of that. Toroidal B. And there is another colloidal magnetic field. So the name suggests, so it is lies in a pole. Okay, the same thing. The same thing. If I draw, okay, uh, if I draw, so if I draw like so, if I draw, so suppose this is a toroid, okay, so it acts upon this direction, it acts upon, it acts towards the poles, okay, towards the poles, it acts towards the poles, unlike, okay, poloidal B, unlike toroidal, but toroidal actually acts, uh, okay, toroidal actually acts like this, okay, I should use some different color, like this, no, this toroidal, okay, toroidal loops, so toroidal, toroidal, anyway, my point is toroidal and toroidal manipulation, so there can be conversion in turbulent dynamo, there can be conversion from toroidal to poloidal, okay, there can be some conversion from toroidal to poloidal. What this tool can do, oh, interesting. Anyway, so there can be conversion from toroidal to poloidal or pole-toroidal, okay, due to the differential rotation. If the rotation is, you know, if the rotation axis is coming out, or here, rotation axis. So rotation axis, if the differential rotation is there, so it can have toroidal magnetic field. So option B is the right answer, as differential rotation can generate toroidal B from poloidal B. Okay, so I think we have understood. And the last one is question number 10. For a kinematic dynamo, velocity field is steady, does not affect evolution of magnetic field, effectively poloidal D evolves independently of the magnetic field. Okay, so basically straightforward answer. For a kinematic dynamo, velocity field actually evolves independently of the magnetic field. Option D is the right answer. So I hope I have been able to answer your queries and all. So that's all for the whole course. Okay, let's look at through the question number 1. So temperature of core is below cool temperature. Okay. Turbulent viscosity responsible for solid body rotation of the slowly rotating stars. Okay. Reynolds stress is 0 when velocity at each point of fluid is uniform. Ivoshnikov Kaiserman energy varied for isotopic energy WS, the non-zero main magnetic field. Okay. Energy Casper inertial energy turbulence is due to interaction between counter-propagation alphanic wave packets. Okay. What is strange about isotopic field? It had lasted much longer than 3 times as before because the core had lasted more than 0.3 million years. Steady magnetic field which is symmetry about an axis can never be sustained by steady velocity field which is also symmetry about the same axis, or can be sustained by steady field but non-axis symmetric velocity field. Okay. There is no plasma motion inside the inertia of Earth, then estimate. So I have estimated this coming in theta 10 over 6 years, which is close to the theta 10 over 5. So the option you should select as A because there is no value of theta 10 over 6. Otherwise, you can select that. A turbulent dynamo proton magnetic field can generate a toroidal field by differential rotation. So this is the rotation axis, right? So because when it is rotating, so this whole toroidal thing which becomes an imagine. So it is rotating like this. Okay, a differential rotation is there. So this whole toroidal thing will become like toroidal. Okay, this is how it can generate. Equal kinds of good simulation, I guess, or actually I worked a little on that field, so I simulate. Hope there is some time, then I can share some simulation code or something. Show you, but for now, that is not the scope of the course. Otherwise, we have to show. Okay. For a kinetic dynamo, velocity field is revolves independently of the magnetic field always. Okay. So this is it. Okay. So that's all for now. Thank you.